Okay, so let's go ahead and start this out. We've got our reactant. We'll call this our red path and our blue path. Okay, so this is the intermediate product. Right, what we're looking at is an energy diagram behind what's happening in this reaction. The intent behind it is to get a visualization of what's happening between those transitions and between what product we expect out of a reaction. In this case, it becomes kind of a toss-up. In future cases, it becomes less of a toss-up and becomes very particularly one product. So you have to be able to know where it's coming from first to be able to dictate what's happening afterwards. Okay? So if we started off with our reactants, because we don't know roughly where they are, we'll just give a little well. There's our reactants. If we go through and look at our intermediates, because those are probably the easiest ones to evaluate because they're charged. Everybody's used to looking at a charge structure and saying the reactivity is where the charge is. Okay? So in this case, we're looking at that positive charge. We have a red intermediate and a blue intermediate. Okay? Which of those intermediates is more stable? The blue one is more stable because it is a secondary carbocation. We're looking at 1, 2 carbons connected to where the carbocation is. Make sense? Which means it should be lower in energy than the red intermediate. Should it be higher or lower in energy than the reactant? Should be higher because it's charged. So I'll just kind of arbitrarily show this. There's our blue intermediate. The red intermediate should be higher in energy because we're looking at a primary carbocation. It's only connected out to 1 carbon. Okay? The next part, looking towards our products, and this one becomes much more challenging. Okay? We aren't used to evaluating product energies. We're used to dealing with intermediates because they're charged. As soon as we move into comparing neutral structures, everything gets a bit haywire and we start to kind of panic. Okay? Before we panic, look for the differences within the structure. Right? We've got sigma bonds and pi bonds. Which of those are the most likely to evaluate? Why should we evaluate the pi bonds before we look at the sigma bonds? Okay? They're higher in energy. We go back to the intermediate. Remember when we first drew this out, I was like, haha, you were wrong because you didn't look at resonance. Why did we need to look at resonance first? The charge was there regardless of whether or not resonance was there. Why did we look at resonance before we made the nucleophilic attack? What electrons moved in the nucleophilic attack? In the nucleophilic attack, that's looking at the bromide with a negative charge, right, attacking the carbocation. That was our initial statement, right? And I said, whoa, we can't do that yet. We need to look at the pi bond first and look at resonance. Why did we look at resonance before the nucleophilic attack? What electrons were in resonance? The pi electrons. What electrons are coming from the bromide? It's our sigma type electrons. That bromide is sp3 hybridized. Okay? So if we just evaluate raw energies, it makes sense to evaluate that pi bond first. Right? Secondarily, why else should we evaluate the pi bond instead of the bromide? Which am I more concerned about? Geez, that would be really weird. I need something less weird. I'm stuck with really weird, so we'll just have to use something else. Which would you be more concerned about? Yeah, that's still weird. Which is closer? Let's try that. The pi bond or the bromide? Closer to the carbocation. Why is the pi bond closer? It's physically attached to it. Where's the bromide? Somewhere else in free space. For it to react, it must be next to it, but it has to transverse that distance to get there first, then it can react. The pi bond doesn't have to transverse this big distance. It's there. It can just move across. Does that make sense? So the pi bond is higher in energy and proximity-wise much easier to react. So it makes sense to look at resonance first. Okay? So when we get to our products, we want to evaluate the stability of those. We're going to start with looking at the pi bond because it's the highest energy source of electrons in that structure. Pi versus sigma everywhere else. Are the pi bonds the same in those products? No. Okay. What makes them different?
Their location and what they're attached to.
Okay. The biggest argument is going to be what they're attached to. Okay. Said using fancy terminology, that would be how they are substituted. Okay. Confusing substituent was that. Easily done. Okay. So how are they substituted? Well, in the first one, how is it substituted? What we're referencing is each of the bonds that comes off of a carbon of that pi bond. Okay, there's 4. Well, there's also 4 in the bottom one, so that's not a difference. Where's the difference? I don't want to go as far as structure. Does that make it easier to see? The number of hydrogens connected to it. We had 3 hydrogens versus 2 hydrogens. Right? How is that going to change the energy of the molecule? Does hydrogen do a whole lot to change the energy? Why not? Itty bitty bitty. Not really going to do much. So we really aren't looking at the hydrogens. What are we looking at? We're looking at the R groups connected to it, the things that are not hydrogen. And in that case, we're looking at carbons. How many carbons in the blue structure? 1. In the red structure? 2. How does that affect the reactivity of the pi bond? Okay. The analogy I like to use, which is very hand-wavy, but it works, for those electrons to react, what must they do? The pi electrons. They have to come in with contact with something. Come in with contact with something where? Outside the structure. So what do those electrons have to do? Get past things that could be blocking them. What things could be blocking them? Well, how about the 4 atoms that are connected around? Well, there's going to be 4 atoms regardless. We can't do anything about that. But what about the identity of those 4 atoms? In the case of the blue position, what happens? We have 1 carbon. What is the difference between that 1 carbon and, say, the other hydrogen? We could say bigger. What does bigger mean? More electrons. What happens is the pi electrons try and go out towards the carbon. There's more steric influence, and that shuttles the pi electrons back into the pi bond. What happens in the case of the red one? Happens twice as frequently. If the electrons can't leave the structure, can they react? If they can't react, what does that mean about its energy? It is lower energy. It is more stable. So we can draw our red product lower in energy. It should be lower in energy than the reactant because we lost a pi bond. Okay? And our blue product, we can draw on our blue product. If we finish this out and drew on an energy diagram, or finished our energy diagram, a couple big things come out as differences. First and foremost, the activation barrier for the first step is much higher for the red one. Why would it be much higher? The intermediate it's going to is higher in energy, which means the activation barrier has to be even higher. Okay, which means that first step now has a drastically different rate between those 2 types of mechanisms. The other big difference is if we look at the products, right, the red one is significantly lower in energy than the blue one. Okay? Because it is a lower energy product, I can refer to it as the thermodynamic product. I cannot refer to the blue intermediate as a thermodynamic intermediate. Okay? Why not? Because that's confusing. Don't do that. Okay? We will only refer to the thermodynamic and kinetic products, which means the final neutral structures. Okay? So what does the intermediate tell us? Which product is more likely to form, the thermodynamic one or this blue one? Why would the blue one be more likely to form in this picture? That first step is really easy to clear that activation barrier because it's lower in energy. Why is it lower in energy? Because the intermediate was more stable and lower in energy. That means this blue product happens faster. Because we're now talking about speed, I can bring in the idea of kinetics. Okay, so I end up with a kinetic product and a thermodynamic product. Those products, or which one I get, will heavily depend on the conditions of my reaction. Okay? The simplest condition we can deal with at this stage would have to do with how much energy we put in. Okay? The reaction temperature. If it is insanely hot, which product do I form first?
The thermodynamic.
Which product do I form first? First is an order of sequence, right? That means the one that happens fastest, which is going to be kinetic. What if it's really cold? Which one happens first? It's the same thing. The kinetic will always happen first, period.
Even with the higher temperature?
Even with the higher temperature. And yet, if I go and look at my reaction flask, after I've run it, stop the reaction and look at the amount of products, at that high temperature, I find very little kinetic product. Why? Didn't we just say the kinetic product should have formed first? At those higher temperatures, I still form the kinetic first, but that reverse reaction is more likely to happen with the kinetic. So if we drew this all the way out at high temperatures, and this is going to look ugly right at the very bottom of this, we start with reactants, which will immediately go to form the intermediate for the kinetic, which will then go to form the product for the kinetic. Problem with that, or not problem necessarily, is that that reaction is reversible. Okay? So we could show that with a double arrow, or we could just say, well, it could also go back to the intermediate, which could go back to the reactant. Okay? If that's the only reaction we were looking with, that's not a big deal. And I'm now oscillating back and forth between forming the product and just having no reaction happen. Except what happens also at that very high temperature?
It goes back to the thermodynamic.
Some of my product, or some of my reactant, can go to form the thermodynamic intermediate. What is now problematic with that equation, or that reaction?
You end up with a thermodynamic product.
That one is not reversible. Because the activation energy is so much higher. And maybe that first step is reversible. That's not a big deal. But what step is absolutely not reversible? The one where we go to form that product. So if we look at this all the way through, and we can even throw reversible in there, we think back to all the equilibrium stuff we learned in 152. Okay? Our products have shown up now twice, red and blue. Okay? What product would I expect at this high temperature? Yes, I form the blue, but then what can the blue do?
Go back.
It can continue to move, depending on our perspective of forward or back. I'm trying to make this linear. It could go back to reactant. Some small percentage of the reactant goes to form product. Because that's not reversible, what happens with that equilibrium? For more intermediate, which means the reactant slowly decreases. If the reactant slowly decreases, what happens? I form more reactant from the intermediate of the blue. Well, if that one decreases, what happens to the product of the kinetic? It also decreases. And it decreases all the way back until eventually all I have is thermodynamic product. Okay?
At high temperatures.
At high temperatures. When I switch to low temperatures, now what happens? Well, which reaction happens first?
Still the kinetic.
It is still the kinetic. Is the reactant to product still irreversible? It's low temperature.
No.
No, it's still irreversible. It can't reverse. Okay? What happens to the likelihood of forming reactant to thermodynamic intermediate?
Very low.
So low that effectively I don't form intermediate. If I never form intermediate, I don't care about whether that last step is reversible or not because it can't happen. I don't have enough intermediate. What meanwhile happens with the kinetic product? It goes to form the intermediate and then it forms its product. Is that product reversible? If it's the kinetic at low temperature,
It's not reversible.
it is not reversible. How does that change the diagram?
You just stop there.
It stops at the product. I can't even progress through the reverse reaction. That means the only product I end up with is now going to be the kinetic product. Which is really, really neat and really, really confusing. Okay? We're looking at temperatures controlling those reactions. Okay. Temperatures controlling these reactions. Okay. Is you just saying temperatures because I said something else? No? Okay. Just checking. Temperatures controlling those reactions. Is there anything else that we could do to change the energy of those intermediates or reactants or products? We could use a catalyst. What else could we do?
You said something about poison catalyst?
Don't bring that in yet. Thankfully, we won't ever have to do that, actually. So let's leave that out. What if instead of using HBr, I switch to sodium bromide and water? Do I still have the nucleophile? Yeah. Do I still have a hydrogen source? Yeah. How would that change the energy diagram?
It wouldn't.
Okay, what was it previously? HBr versus sodium bromide and H2O, right? Okay. Let's make it a little bit easier. Instead of bromide, let's make it chloride. So HCl versus NaCl and water. Everybody okay with that? Okay. So here's the switch on this. That's why we're trying to bring this in. I have a container of HCl on the counter, and I have a container of sodium chloride and water. Which one do you want splashed on you? Sodium chloride and water. Why do you not want the HCl? Because the hydrogen. Well, why do I? Water has hydrogen too. I don't accept that. Hydrogen ion. Why does it have hydrogen ion with HCl? Dissociates. Why is it dissociating?
It's reacting with hydrogen.
It's reacting. If it's reacting, what does that mean happened to its energy?
It's high.
It's higher. If I switch this to water, what happens to the reactant energy? It drops because water is more stable. If that reactant energy drops, have I changed the activation barrier through here? Yeah,
It goes up.
significantly. And the reactant energy is now so low that the reaction doesn't work. Okay, number one. But which product would I expect to actually form? probably the kinetic, and probably only the kinetic. Why would I never expect the thermodynamic, even at high temperatures? I've dropped the energy for the reactant so low that the activation barrier for the thermodynamic is now virtually impossible.
Not even
Okay.
at higher temperatures?
Not even at higher temperatures. More than likely, I'm going up to high enough temperatures that I'm there where I have the energy to do it, but also at that energy, what else do I have the ability to do? Well, a bunch of other stuff, like completely destroy the carbon backbone. Okay. So we do have limits on our temperatures, because we could go hot enough that, yes, things now work, but not just the reaction we wanted to work, also 5 other ones. So typically, when we run reactions, we run them at relatively low temperatures to limit those other reactions. Okay? In this case, what we did was either look at the temperature or change the reagents. As we move further through the semester, that's one of the things that we'll talk about, looking at temperature effects and potentially reagent effects. The video that's due next Sunday, Kinetics and Thermodynamics, looks at, I believe, 4 examples of kinetics and thermodynamics. One of them is this one. You've now seen it. Okay? One of them is the Diels-Alder. Another one is enolate chemistry, and another one is alpha-beta unsaturated carbonyls. What? Yes. All 4 of those are reactions we will talk about this semester, and they all deal with this concept of kinetics and thermodynamics. Okay? You have the fundamentals to now grasp what's going on with those. That doesn't make it easy, okay? But it sets you up with a way to at least think about the chemistry as opposed to just saying, well, I've got this alpha-beta unsaturated carbonyl, which we can barely even say, okay? And this reagent. Okay? Well, I'm going to memorize this reagent does this every single time. Okay? Or I can say, well, that reagent doesn't have enough energy, the thermodynamics aren't allowed, and I only get the kinetic product. Or I only get the thermodynamic product. Okay? So what I'm trying to do is set you up with the tools to be able to find those patterns. Okay? It's hard. It takes time to think about and process. We excited? Yeah, let's do it. Okay? So, why would we expect the pi bond to act as a base? It has extra electrons. The pi electrons are higher in energy. What things have electrons? Bases and nucleophiles. How strong of a base or a nucleophile would I expect that pi bond to be? Why should it be weak or not good? Not charged. Okay. I could draw out then, let's take a look at another example. Let's draw water. Is water charged? Which one's the more active base? Water or the alkene? Why? Partial charge, so we could start to look at dipoles. I was not hoping for that answer, because that's a better answer than what I would have come up with. Shoot. And I can't come up with one that's not going to get you partial charges. No, actually, that does work. Let's work with that. Okay. Why does water have partial charge but the alkene not? A difference in electronegativity. We have oxygen and hydrogen versus carbon and carbon, which means nonpolar. Those electrons are equally shared. They may be high energy electrons, but they're equally shared, which then means they aren't very reactive as either a base or a nucleophile. So for me to get them to react, what do I have to do? I'm going to have to put energy in. I could put energy in as a really high temperature, or I could change my reactant. If I want my alkene to act as a base, which hydrogen source makes more sense to react with it? Water or HBr? HBr because it's a higher energy acid than water. So thinking about the reactivity of those pieces can help you predict whether that reaction even works. Okay? That's nice. Okay, what if we had an alkyne? What's different about the alkyne from the alkene? 2 pi bonds. Okay, there is a hydrogen there. We could potentially evaluate it as acidic. And I would argue that your statement makes awesome sense if I do this. Anybody blink? What did I do?
You got rid of the HBRs.
Okay, so if we bring that back, does it make sense to reference that hydrogen as acidic? You're shaking your head no. Okay, why? HBr is more acidic. Okay, so yes, we can reference that. Acetylene has its own chemistry associated with that. Hydrogen becomes acidic because is it charge? Okay. If we go through to evaluate why is that hydrogen become more acidic, say, than if we had just an alkane. Versus, sorry, it's a bit sloppy. Why is the top one more acidic than the bottom one?
It's more likely to react with hydrogen.
The top one's more likely to react? If it is more likely to react, will it donate the hydrogen?
No, it would take it.
It would take it, which would then mean Mo is wrong. Mo's right, though. Sorry. How would we evaluate which of those was more acidic? Charge. So we could evaluate higher in energy. How do we know higher in energy? Well, the first thing we would evaluate is charge. Are they both charged? What charge are they? What was it? Yes, it is either positive or negative. I completely agree. Does it make sense to evaluate the positive charge? Why not? It's the same charge. Okay? Or on the same atom. If we move over to the other structure, we say, but isn't it the same atom there? It's still carbon? Yeah. Is that carbon different? Okay. How is it different? Okay, so it's looking at the literal pictures behind it. Let's go back to the rules. Okay, my students aren't allowed to forget this. If you haven't had me, you can kind of play it soft at this point. We start with charge. The next thing we evaluate. Size. What is the atom holding the charge? Carbon and carbon. Is there a difference in size? No. So we move to electronegativity. Is there a difference between carbon and carbon? No. So what do we move to? Shh. What do we move to next? Resonance. Is there a difference in resonance? That's trickier. You should play around with it. Not really. There isn't really any good resonance for either of those structures to stabilize that negative charge. Okay, the next one would be inductive effects. Do you see any electronegative atoms? No. So induction doesn't help, which moves us into the very last category. And in that last category, it becomes a big mess of things. The more important, or usually the most important one, is hybridization. What is the hybridization of the carbon in this first one? It is sp versus the bottom one, sp3. What is the difference in hybridization? 2p orbitals. A lot was also a good answer. I like that. This one has what? More or less p? Less p. It decided to go before the class. Sorry. I apologize. Not really, because it'll probably happen again. Okay. What is the difference between S and P? A couple of squiggles. Also got rid of that answer.
The more S character an atom has, the more stronger it is.
Okay. So we've got a memorization associated with that, which is good. The more S character, the more electronegative it is. Why? More S character is now ultimately looking at the difference between S and P. S is closer to the nucleus than a p orbital. So if you have more S character, the electrons are literally held tighter. Is there a theory that explains how electrons are held to our nucleus? Electronegativity. I didn't hear what you said, so we'll just assume it was electronegativity, because your face made it sound like it wasn't. Okay? So, electronegativity. The sp hybrid orbital is more electronegative than the sp3. So if we go back to our theory, when we evaluate our charge, one of our things was looking at electronegativity. The more electronegative an atom is, the more likely it holds the negative charge. It can stabilize it better. If that negative is more likely to form, what does that mean about the presence of hydrogen? It is also more likely to form. Acetylene is more acidic than your standard alkene. Okay? So that is evaluating a difference with the alkyne. Unfortunately, that was a massive sidetrack, but useful. What do we still have in the alkyne? A pi bond. What do we have in HBr? A still reactive positive hydrogen. What can happen? It can attack. And I get the exact same reaction. No difference. The basic chemistry is still there. This isn't a memorization of a new type of mechanism or a new type of reaction. It's the same thing. Okay? What if we switch it up to this one? Massive curveball. Should we go a little bit easier first? No. Okay, then tell me the answer. If you can tell me the answer before I actually draw the easier version. So based on your lack of answer, I'm actually going to say you needed the shorter version, or the hint. What's the product? Yeah, what's the product for that bottom reaction? Okay, let's take 5 seconds for a little bit. Somebody go on. This is a trick question. Yes, it is. I don't care. Draw your answer. If I don't think you're drawing an answer, I'll turn it into a quiz. Draw what you think the answer is. For the second one, not the first. I drew the answer for the first one. Do the bottom one. I like it. Oh, no, stop it. You did good. Right. So, I like it. You saw that we added an OH, right? Got rid of the pi bond, we put an OH. Where did the OH go here?
That carbon.
Okay. Where did you put the OH?
I put it on this carbon.
Okay, why?
I don't know.
Okay. No, that's fine. So, part of this would be evaluating your mechanism. The first step is that the hydrogen gets placed on this. We would form a carbocation. That carbocation can then react with the water, right?
Yeah.
Okay. If it does so, where would the carbocation most likely form in this structure? Where's the most stable place for it?
It's right there.
Which would mean the water should go.
Yeah. So does this go right here? Okay.
Unfortunately, it's still wrong, but good. It's good.
Still wrong.
We'll talk about it.
Okay.
If you haven't learned it yet, yes, I am a horrible person. I'm not sure it was supposed to be fun. I think it had to be funny, right? I think it was supposed to be a joke. We should recognize that acid is reactive. I need to neutralize that H+. I'm going to generate that as a carbocation intermediate. Okay? And I want the positive charge in the more substituted position. Okay? Because that is more stable. Water could then theoretically attack, do some other acid-base stuff, so a couple mechanistic steps later. And we would end up with this structure. Ish? How many people got that? Okay.
I was
Close. Okay, I'll kind of accept that. Is that the correct answer?
Doesn't that keep going?
Yes. What does it keep going to do?
Pi-bond reacts again.
Okay, so let's work with that. We have the potential for this continuing to go through this process because, as Cass is pointing out, there's still a pi bond. Well, if there's still acid, shouldn't it react with the pi bond? Okay, so what you're suggesting is that we then go to this structure. Yeah?
Yes.
You're committing. I like it. So, what do you guys think? Which answer is the correct one, red or purple? Trick question. Trick question. Neither. Damn it. So, a couple pieces of information come out of this. We'll address both of them. From my students, you should recognize this. What functional group is that? An alkene. If you're not my student, maybe you recognize this. I don't know. It depends on the level your instructor went into. What is that? That's an alcohol. Okay. These are not independent structures because they're connected. Notice my circles are overlapping, which means these are not two different functional groups. This is one functional group. I can't call it an alcohol alkene or an alkene alcohol. I want to combine those. I combine them to become an enol. Enols are insanely important functional groups that we will see again and again and again this semester. Okay? If you had the classic chemistry class or the classic organic experience with this reagent, okay, and I did cheat a little bit, usually you see HgSO4, okay, and that might cause some of you to trigger what the actual answer is. The actual answer is the ketone. Okay, it goes straight to the ketone. Why? The enol chemistry is unstable. It rearranges the electron density, which we can talk about at a later stage, to form the ketone. So why do we not see this top structure? Well, that top structure was made assuming we had the alkene. Did we ever have the alkene? No, we had the enol. So already that's a questionable step for running on. Turns out that structure is still valid. It is what is known as a hydrate. Any idea what hydrates do?
They take the water off.
They become the ketone. Okay? And so when we first look at this reaction, we go, oh, this is an entirely different reaction. It's not an entirely different reaction from our standard electrophilic addition. It's still following the same patterns, but what we have to do is pause and evaluate with our intermediate structures and decide what's going on there. Okay? The chemistry there is not easy to track. It really requires some knowledge of seeing it to recognize that it would be more stable as the ketone. Okay? This is why students often just accept, well, I'm just going to memorize the reagents and move on. Okay? If that's literally all you want to do, there's nothing I can teach you. Because that's all it is. You just memorize reagents. Okay? So what I'm going to try and do is point out where those patterns are, and we'll work with that. Make sense? Ish? Okay. So we're going to throw in a dash of radical chemistry in here from chapter 25. Some things I just want you to watch out for. These are all examples of radical species. Okay? This first one, we evaluate this, is really just a fancy way of saying some R group connected to an oxygen that is a radical. Are radicals stable? No. What do they want? Another electron. So what if I put another structure like that next to it? What do I have? I have ROR. ROR is a giant red flag for radical chemistry. We have an oxygen-oxygen bond. The oxygen-oxygen bond is insanely weak, and given either heat or light, that bond will cleave homolytically, is the correct word, I believe, to give us radicals. Those radicals can then do all sorts of nasty chemistry. Oxygen as a molecule is actually a diradical as well. Okay? This is why it is reactive. Okay? We have unpaired electrons. Bromine has radicals, and you can also see carbons as radicals. Okay? Ultimately, the reactivity of radicals is cations. Okay? If you see a reaction that you think would be a radical reaction, treat it like a carbocation and do whatever you think we would normally do, but do it where the carbocation would be. Okay? Our big reaction summary with alkanes, there's really only one, bromine and light. Why do we not look at the chlorine in light one? It's literally drawn up there. Why you guys should be glossing that over? Is it the same thing? Do I get the exact same result? Bromine with light versus chlorine with light? No. What's different? I get a bunch of different products. Why? Chlorine is not selective. Bromine is. So that means synthetically we ignore chlorine. If I want to run a reaction to make something, let's say I want to make sweaters. Okay, so I take a bunch of yarn and I start moving the yarn around to make sweaters. Half of the yarn turns into shoes. Was that a really good sweater maker? No, why not? Because you made shoes, not sweaters. Okay? Same thing is happening with chlorine. Chlorine goes through to react, and instead of making just one product, it makes 5 or 6. If you only want one, that's not a very good yield. Okay? Alkenes will do some tricky chemistry. NBS in light will do a bromination, so it'll do a substitution for the hydrogen, but it's doing the hydrogen at the most substituted position. Because it's radicals, you can get all sorts of weird rearrangements. Why would we expect rearrangements with radicals? What did we say radicals should be equated to? Carbocations. And what can carbocations do? Rearrange. So you've got to watch out for rearrangements with radicals. Okay? Notice again, red flags, we've got light, and down here we see roar. Okay? Those are your big signals for radical reactions. Those of you saying, well, Mike, you're telling me to memorize these, and you told me not to memorize anything else. Yes, this is 3 things, not hundreds. Yes, plural. Okay? It just simplifies the radical chemistry if you just go through and memorize these. Okay? Why am I concerned about looking at it? Let's take a look at this first reaction up top. HBr with roar and an alkene. Okay? What happens? You should be able to draw the products because I just showed you what would happen on the previous slide, right? Didn't you memorize that already? Okay. Previous slide. What do I expect? There's my HBr and there's my roar. What changed? I think I accept least substituted. You're saying the bromine goes to the least substituted side. What went to the most substituted? Hydrogen. We are adding HBr across the pi bond, but we're adding it in the opposite direction we would typically expect. This is where someone went through and said, well, that's not what Markovnikov said. And so they said, oh, let's call it anti-Markovnikov. That's literally it. That's anti-Markovnikov. Why? Because someone observed it. That was it. Okay? So, what's our product for that top reaction? Can you draw? Yes, you can draw it. As in you want to draw it and show me? Is that what the question was? Yeah? Someone want to show me? We could always just make Cass draw things. She likes drawing stuff. Where's the bromine go? The terminal side, there's my bromine, right? Ta-da! Magic. There's our answer. Okay. What happened in the process of that reaction? Okay. A whole crap ton of stuff happened. Okay. So the first thing that happened is we ended up with the radicals. Radical's not happy. What does that radical react with? It could react with another radical, but one of the things that's nice for us as humans is that radicals are very low concentration. If they're high, what happens? Death. Okay? So low concentrations of radicals, so the odds that another radical impacts another radical very low.
Positive cations?
Do you see any positive cations? Okay. The most likely thing for that to react with would be the most reactive thing present in solution. What's the most reactive thing after the radical? HBr. Okay. Which is more reactive, the H or the Br? The H. So what happens? That radical shares one electron causing that bond to break. The result is we form ROH and Br radical. What does that radical likely react with now? Okay. Believe it or not, it most likely reacts with HBr. That's not very productive. Sorry. So let's go for the pi bond. Okay. So a single electron comes out, single electron comes out. Which means we are forming a bond between the bromine and one of those carbons. Which carbon? Why do you want to put it on the terminal? Fair enough. What bond is reacting with that bromine radical?
Carbon.
A decent answer, but I asked for bond. The pi bond, how many electrons are in that pi bond? 2. How many electrons came out to make the bond with the bromine radical? Where did that last electron go? To the remaining carbon, right? That remaining carbon needs to act like a carbocation. Where's the carbocation most stable? At the tertiary position. Why did the bromine go to the primary position? Because the radical forms on the more substituted position.
Well, you said it means act like a carbocation, it means anion.
Carbocation. Yeah, radicals are weird because they're one electron. You would think they are halfway between an anion and a cation. They act more like a cation than an anion. Okay. Now what happens? What's the most likely thing for that species to react with? More HBr in solution. There's nothing for it to react with itself. The odds of finding another radical in solution, very, very low. Radicals aren't stable and tend to kill each other very fast. Okay. So more than likely you would encounter HBr and we'd end up with a final product. Oh my God, that was a lot. Fun part with that is that that wasn't the question. The question is actually the one underneath it. What's different? Why is that a problem? So when this goes through and reacts, we get OR, and then we'd have a radical out there, right? What does it react with? Remember, when we run our reactions, it's not a single molecule of each of these. It's a solution of them. Probably billions upon billions of these. So what also happens to be nearby this structure? Not more radicals. Again, this is the tricky part. Our radicals are insanely low in concentration. More. It is red. You're right. I did not recognize that. More of our alkene. So now what happens? What does it form? What was the face, Taylor? What do you not like? Looks ugly. Yeah, I'll redraw it in a second to make it look pretty. What's the problem with this product? It's another radical, which means It's going to react again and again and again. And what we've done is formed a polymer. Yay, polymer chemistry. Radicals run under polymer chemistry. Ultimately, the big point on this is what started this. What reacted with the alkene? Ignore the radical for the moment. What reacts with this alkene? Another alkene. Can alkenes react with alkenes? Not typically. We need something to cascade it and start it off. Okay? Are there cases where alkenes can react with alkenes? The answer to that one is yes. Why is that slide there? Okay. Why am I going with this as alkenes react? Oh, because I gave you answers. That was nice of me. Look, pretty structures. See? Much nicer looking. Okay. Why do we want to evaluate that alkenes can react with alkenes? Okay. What happens if we combine this alkene with the alkene we started class with? What was the alkene we started class with? Well, I don't know. That was like an hour ago. That was exactly 51 minutes and 10 seconds ago. What is different about this blue structure versus this one? 2 pi bonds. What is special with that 2 pi bonds? It is a conjugated system. This conjugated system could react just like this could in a polymerization reaction, except now instead of there being 1 pi bond, there's 2. You can get branching within the polymer chain. Okay? This makes drawing it an awful mess, so don't stress about that. Okay? So one of the big things that I want to address here is what if we allow the pi bond to potentially move? Okay? So this top one up here, drew it as a nice straight line because that looks pretty. Couldn't I have drawn it like this? Yeah, right?
Is that considered resonance?
It's not resonance.
It's just an acceptance.
Okay. All it is a secondary rotation about a sigma bond. Okay? And I hear a reference to cis. Well, cis and trans refers to ring structures, things being on opposite or same sides of the ring, or opposite and same sides of a double bond. Did I do anything to the double bonds? No. So I can't call this cis and trans.
But something has to cause it to be that way.
We'll address that too. We did a rotation there. That rotation is allowed. Okay? And there was a suggestion, the one drawn in red was what? What'd you say? Didn't you say it? Yeah, cis. That this one is cis. Well, if this one's cis, somebody else, what do you think the top one is? Trans. Okay? But cis and trans don't make sense here because we haven't affected the double bonds. We aren't allowed to rotate those double bonds. So this is not cis and trans. What did we rotate? A sigma bond. And sigma begins with S. This is an S cis or an S trans. So those of you who read the book are like, what is that S talking about? It's the sigma bond in your structure. Now I can refer to that to call attention to it. Is that rotation important? We did name it, so yeah, it is important. Why does it become important? Well, what if I switch to this system? Okay? And we could do radicals and see a polymerization. We could also entirely remove the radical. And now we say, well, that shouldn't react at all. Fair enough. It says no reaction, so we're just going to mix those and nothing's going to happen, except something did happen. What happened? Something goofy and weird happened. Why did that happen?
Because you can change the trans to a cis. And then,
This S trans, what happens if I take that and make that S cis? It is higher in energy. We can evaluate that. But now when I change that orientation, what does that start to look an awful lot like?
Diels-Alder.
The product that I'm making out of this.
Oh, yeah.
I would fully expect this to not react, which is why when someone went through and did it and it did react, what could they do? They can stamp their name on it because everybody said it shouldn't react. because they can now prove that it did react and explain it, they get credit for it. Okay? And there's all sorts of pieces that go into the Diels-Alder reaction. Okay? So you'll hear reference to this S-cis and this S-trans. Okay? And believe it or not, yeah, you probably can believe it, the Diels-Alder reaction is a mess of different pieces. Okay? It takes everything you learned in first semester and jams it all into one question to make it a giant mess of terminology, okay? Structure, models, stereochemistry, it all shows up. Okay? It is a neat reaction to play with, but it takes way too much time to go through and evaluate. Okay? So how do we address it in this class? So here's our basics. We look at our reaction, and we decide what changes happened. Okay? This basic format should happen for every single new reaction we do. Okay? It won't, because it takes too much time. Okay? So what are the changes that happened? What bonds broke?
So the two double bonds.
Okay? We broke double bonds. Okay? Arguably, we actually broke all three of them. And then what did we do? Okay, we made one new pi bond and two new sigma bonds. Okay, that's a lot of things changing at once, which means mechanistically that's probably a nightmare to resolve, because we can really only arguably do two, maybe three things in the same step. That's 6 different things exchanging. The argument that I've made in lab, so for those of you that aren't in lab, is that the pi bonds never broke. Okay? Which is kind of a weird statement, but I think it makes sense because I could draw that structure like that. Do you see a pi bond? No. You may not like it, so you can make faces all you want. Okay? But what is that new structure I drew? As a hint, the answer I'm fishing for has to do with that magic arrow in between. It's a resonance structure. They're the same thing. So arguably none of the pi bonds broke. It's just a question of how the charges aligned to make the new sigma bonds. So really all that's happened here is the formation of 2 new sigma bonds. So the question becomes, is how did it happen? Did they all happen, or did they happen stepwise or simultaneously? Okay? Depending on how much you've read in the textbook, you may or may not know that answer. Okay? One of the reasons why I don't want to reveal it yet is because that's what the entire lab is based on. Okay? So we would have to evaluate by experiment which mechanism made the most sense. And for those of you being like, wow, this sounds really hard, you've already done this in first semester. When we look at a substitution reaction, there were 2 mechanisms, SN1 and SN2. What dictated those? Did you do the 2 things at once, SN2, or did you do them stepwise, SN1? What happened as repercussions of those mechanisms? Well, in the SN1, you end up with 2 possible products. In the SN2, you end up with only 1 product. The same concept applies to Diels-Alder. Diels-Alder gets a special name associated with it instead of just substitution because only one of them is valid. Okay? So all of those answers are summarized in one video. It is in the play posit, so you can watch that. It is actually assigned to be due next Sunday, called Diels-Alder Answers, I believe. Within that play posit video, it actually summarizes and it explains all the pieces, which is a giant mess to understand. Right? But it also provides a summary side that just says, you just want to memorize, this is what you got to memorize. Okay? Because it is very difficult to process. I have no problem sitting down and working with anyone by going step by step through it with model kits to evaluate everything. It's a mess. Okay? But we can do that. For those of you in lab, you don't get a choice. For those of you not in lab, you could just memorize and you'll be okay. Okay? Kind of, sort of? So let's take a minute to breathe, break. Nomenclature. Okay? This is everything there is about nomenclature. Okay? Sort of. It covers roughly 70-80% of anything that could be asked as far as nomenclature goes through the entire semester. Okay? The number of carbon chains you need to memorize, the basics on how you would put together a name, okay? Some halogen information. If you have substituents off the main chain, you get the YL. You have to specify location numbers with the smallest number. And then the fun one is naming each functional group. In the middle, your alkanes, alkenes, and alkynes are kind of your root carbon structure. So you will always change the suffix for one of those pieces. Okay. If you have a higher priority functional group, you will delete the E, just one E off the alkene, alkyne, alkane, and change it according to the table above. So if you have an alcohol, like, let's just do it in the corner because it's really easy to see that. Everybody see that lower left? Looks decent. How many carbons? 2 in a chain, so we'll call it S. That's our main root. Okay, now we want to address the hybridization of the carbons. What is the hybridization of all those carbons? They're all sp3 hybridized, and sp3 hybridized carbon gets the alkane ending. So we could call that ethane. And we'd be done and wrong. Why are we wrong? There's a higher order functional group with the OH, which is an alcohol. So our ethane, delete the E and add an OL, and we end up with ethanol. See, easy, right? Okay. Conjugated Pi is the fancy name associated with it. If for whatever reason you see Conjugated Pi pop up again on a test and you're like, what the hell is that? Just ask. Okay? The only reason I reference it by Conjugated Pi, well, there's 2 reasons. 1, that's what it's called. 2, for whatever reason, when I first started at Chandler & Gilbert, it just clicked and I've now remembered it as Conjugated Pi. For those of you keeping track, I said when I got to Chandler Gilbert, I've been teaching organic chemistry and learning about it for roughly 10 to 12 years before that, and never knew it was called Conjugated. Okay, not a big deal, but every so often you want to like show off you know something. That's my show off. Okay, sorry, sometimes it happens. Yay me. Alkenes, we get cis and trans, not the best. E and Z is what you should be referencing it. Chiral, R and S. You may also see plus, minus, lowercase d, lowercase l, capital D, capital L. Entirely different systems. Don't confuse the Conjugated with those. Those are all observationally based. Okay? This is the whole priorities thing, the spinning the wheels and all that fun. Yeah? I'm going to trust that. So easy, right? We're good? Your turn. Pick one. Which one do you want to name? Left, upper left? Were you saying something else?
No, I was just thinking.
Okay, so upper left. First thing we should try and identify is our main carbon chain. That main carbon chain needs to contain our highest priority functional groups. Okay? So if we go through and look at this question or this structure is intentionally drawn this way to trick students. The ACS does the exact same thing. How is it drawn? Well, there's a nice straight carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. One of the answers will have oct in it. And that would be wrong. And that would be wrong because what functional group is that? An aldehyde. And according to our list, sorry for the flipping back and forth, the aldehyde is the 3rd highest functional group name. Okay? Which means the aldehyde must be part of the main carbon chain. With how that structure was outlined, we didn't include it, and that's why we got it wrong. So 1, 2, 3, 4, 5, 6, 7. I'm looking at a hex. Why did I not number out this way? Go 3, 4, 5, 6. Longest carbon chain. Okay? Longest carbon chain is going to be the easiest answer, but I think where you were going, Ishmael,
What's the priority?
was getting the other high priority functional groups as part of the chain. Both answers work. In this case, they worked. You would be right if you wanted to say hept. Okay. So we have a hept. Okay. Next part on this that I would address, well, we actually already addressed one of them. The highest priority functional group was the aldehyde. The aldehyde gets named as al, A-L at the very end of this. Okay. The aldehyde is kind of a special functional group. The aldehyde always shows up where? At the end of a carbon chain, which means since it's the highest priority functional group, it by definition is showing up at position 1. So you can imply the 1. You shouldn't, but you can imply it. Okay, you shouldn't. Why? Because somebody said you shouldn't. That's it. Okay. What is the main hybridization of the chain, or what is the hybridization of the chain? So we'll ignore our primary functional group of the aldehyde and look at the rest of the carbons. Carbon number 2 is sp3, sp3, sp2. We're looking at an alkene in here, so I have to go through and include that in my root. So I'm going to get heptene. I have a new functional group in there. I have to specify the location of that functional group. Where is the alkene showing up? Position 4. So I have hept4-ene, 1-al. Again, the 1 can be optional. Have I named all of my pieces? No. What am I missing? Okay. I'm missing the alcohol. Okay. I would typically call it an all as a suffix. I can't do that because the aldehyde has already taken that spot. So how do I name the alcohol? It's a hydroxy. Its location is at position 7, so a 7-hydroxy. Is there another functional group? We've got the 3-carbon train out here, which is now a prop, okay, because it's all just singly bonded. Propyl as our substituent. Where is that starting at? Position 3. And we can now try and put this god-awful name together. Right? Those substituents now need to come down into the list according to alphabetical order. H comes before P, and I get 7-hydroxy-3-propyl hept4-ene 1-al. Am I right? We have the alphabetical order is correct. The alkene, I didn't specify cis or trans. Do I need to worry about it?
Yes.
Depends. We'll approach that depends in a second. Is that cis or trans? Trans, which means? Sorry, this is how it sticks in my head, but tran-e. It's dumb. And somebody told me, and now I can't get rid of it. Okay. I'd have to include 4E in parentheses at the front. 4E, 7-hydroxy-3-propyl hept4-ene 1-al. Am I now right? Technically, yes, because of a lack of specificity in the structure. What specificity are we referencing? That is technically a chiral atom. I have not specified wedges or dashes, so we can't label it as R or S. We don't have to worry about it. Okay. So the last thing, I know I'm talking too long. When we look at it, do we need to worry about the E, Z, R, S? Okay. Did I need to worry about the RS? Why not? I didn't specify it. Did I need to worry about the E? It was shown. Is there a case where you wouldn't have to worry about that EZ with this structure? Yes. Where's that case? The exam. Why won't you have to worry about it on the exam, potentially? The only way I will ask multiple choice, sorry, let's try that again. The only way I will ask nomenclature is through multiple choice. Look at your answer choices. Does it evaluate E and Z? Then evaluate E and Z. Does it not evaluate E and Z? Then ignore it. Okay? Why? Because I hate nomenclature. Okay? Find the basic patterns in the pieces. You can goof up a lot of the order behind it and still get the correct answer. Get the pieces down on paper. Okay? It takes practice. Keep working through it. And I'm done.